Hello everyone, my name is Thavone. Today our team will present to you the effects of flux residues on the substrate surface in a flip chip package. Here is the list of my teammates. I will give you an overview of our study and my teammates will explain the detail. What is flux? In our study, we concentrate on low residue flux, called no clean flux. It generally have a composition of 2% weight total of solid, 96 total weight percent of alcohol, 1 total weight percent of water, and 1 total weight percent additives. Flux is introduced during the soldering process to promote wetting between the solder and the metallized surfaces. Flux prevent oxides from forming during soldering process. When flux left on the substrate surface, clean flux becomes flux residue. Flux is corrosive. Flux residue should be removed as soon as possible. What are the effects? At low temp, the acid parts of flux do not evaporate. Therefore, solder temperature is a very important factor of the process. In the area with low voltage, small leakage currents can provoke electrical and functional failures. In the area with high voltage leakage, current can cause short circuits. Flux residue may cause the problems such as corrosion of the solder joints, degradation of underfill flow, void formation during the dispensing process, reduction in the adhesion of underfills to the die and substrates, and increased moisture sensitivity of underfills. It may alter the mechanical properties of underfills and the bumps. These may reduce the reliability of the package components. Now I will hand it over to Jasmin.
Thank you, Thavone. I will now cover the effects of temperature on solder flux residues. As you can see, the graph shows the residue left after heating the package. The first bar shows the package before heating, and the others the effect of different temperatures on the residue. The purpose of no clean flux is to automatically vaporize or remove flux when the package is heated. But as you can see, it is not quite true. The traditional BGA package operates at 170 degrees Celsius, and there is still 2 weight percent residue left. Less than 1 weight percent residue can only be found at 250 degrees Celsius. Therefore, it is not possible to remove all residue. Since the previous slide does not show the effect of temperature on composition, thermogravimetric analysis was conducted at 10 and 50 degrees Celsius for flux residue and reagent-grade adipic acid for comparison. As you can see, the adipic acid evaporates at a much faster rate than the flux. For further investigation, FTIR analysis was conducted on residue to investigate chemical changes and the nature of flux as a function of heating temperature. There is no change in composition up to 250 degrees Celsius. After that, there is a significant drop. The ester from the adipic acid remains and becomes a dust trapper and a humidity absorber. The temperature range in the previous slide agrees with the results from the TGA for flux residue chemical compositions. It was also found that the drop in acid weight percent happens due to increased volatilization, which is another indicator of a decrease in leakage current levels. Now, Vivek will take over from me.
Thank you, Jasmin. So I will be talking about the effect of solder flux residue on the properties of the underfill. We followed a study based on this topic, which describes the interaction between the flux residue and the underfill. In an experiment in the study, they blended 2 separate samples of the underfill with the flux, named U of A and U of B, which were dispensed at different temperatures. So the properties that are talked about are thermomechanical properties, moisture absorption, and underfill flow time. When the underfill is contaminated with the flux residue, there is an increase in the coefficient of thermal expansion and a decrease in the glass transition temperature. There is also a change in the storage modulus with and without the flux residue as shown in the table. A thermomechanical analysis was done in the UFA sample. As shown in the plot, with increase in temperature, there is a larger increase in dimension change for the contaminated sample as compared to the pure sample. Samples that contain flux residue have a higher moisture absorption. This is basically due to the lower cross-link density of the underfill. This allows the moisture to invade the underfill. When we talk about the underfill flow time, many factors are involved. The factors are viscosity and the contact angle. The UFA sample has a higher viscosity than the UFB sample. As seen in the plot, the sample with a higher viscosity has a higher fill time as compared to the other sample. The other important factor is the contact angle. The contact angle increases when the contaminated sample with the flux residue. This decreases the wettability of the underfill and hence causes the poor addition of the underfill and the PCB. Now I'll let Manoj to continue the presentation.
Thank you, Vivek. Now we are going to discuss the mechanical issues due to the flux residue. Several mechanical issues are induced mainly due to the flux residue or due to the interaction between the flux residue and underfill. The major mechanical issues that can be found on the surface of the flip chip package are changes in the addition between the underfill to the solder bumps and seeding of bump cracks and deformation of bumps. These issues may lead to reduction in the strength of the package and may eventually lead to the failure of the package. In this slide, we are going to know how the bump cracks are caused. As we have seen earlier, excessive flux residue affects the critical properties of the underfill that protects the bump, namely the glass transition temperature and the coefficient of thermal expansion. In the case of large dies, flux-related voids tend to appear within half of the die, which is usually the side where the underfill exits. This effect is amplified as the size of the die becomes larger and the bump count increases. This seems to be obvious because large dies have higher surface area where the flux residue can reside after the die attach flow process is done. From this, it can also be inferred that as the pitch of the bumps reduces, more accumulation of flux between the bumps can be seen. The glass transition temperature of the underfill is significantly lower due to the flux residue. During the temperature cycling, the temperature at the higher end of the cycle continuously exceeds the glass transition temperature of the degraded underfill. This softens the underfill during each cycle. As a result, the bumps experience a cycle of tensile and compressive loads in each temperature cycle, which may cause plastic deformation of bumps. Due to the increase in the viscosity and flux residue accumulation, the flow of the underfill tends to slow down while exiting the die. Hence, the underfill struggles to flow through the last few rows of the bumps near the edge of the die. In the figure, we can see that the bump is undeformed at the side where the underfill is dispensed, and the bump is deformed at the exit of the underfill. In this slide, the effect of flux residue on the addition of the underfill is explained. Due to the interaction between the underfill and the flux residue, incomplete underfilling exists at the base of the solder bump, forming a fillet-like joint. In worst cases, the underfill may flow around but may not come in contact with the solder bump at all. This phenomenon is called halo effect. As seen in the figure, case A shows a bump with perfect adhesion, and case B shows incomplete underfilling at the base of the bump, and case C shows the halo effect. Now Sahar is going to carry on with the presentation.
Thank you, Manoj. When it comes to the electrical issues and field product failures caused by flux residues, we normally are talking about electromigration and leakage current. In this picture, you see the flux residue under a BGA field effect transistor. When flux residues are left on the printed circuit board, they may react with the moisture and an applied voltage to cause electromigration and electrical leakage. And what is electromigration? Electromigration refers to the gradual displacement of a conductor's atoms as a result of the current flowing through that conductor. As I mentioned before, in electronic packaging, reaction of the continuous film of moisture and the flux residues form an oppositely charged electrode. This will lead to displacement of the metal ions, which gradually reduces the isolation gap and ultimately
cause the electronic short circuit. Leakage current is another consequence of the flux residues. This graph shows the leakage current value versus the amount of flux residue on the circuit board. As we can see, the leakage current increases proportional to the amount of flux residue. Also, it shows that the amount of flux residue decreases by increasing the process temperature. Now, I pass the presentation to Queen from Intel Vietnam. Thank you.
Thanks, Sahar, and here is our simulation part. So as you already know from previous session of underfield property, flux residue left in the bump area can form the void in the underfield layer. So our team tries to do a simulation to see how the impact of this void during the thermal cycle. So the package we built in the simulation is a 3-layer package, a silicon layer, an underfield layer, and one organic substrate layer. So now we will see how the heat is transferred from a 90 degrees Celsius at the top die side to 40 degrees Celsius at the bottom substrate side. As can be seen from the lower picture, for the package without the underfield void, the temperature is distributed nicely and symmetrically in 3 layers. However, as you can see from the upper picture, when there is a void in the underfield layer, there is discontinuity in the heat transfer under the void. Imagine the case of multiple underfield void, there will come the unpredictable thermal distribution in the packet layer, which can cause an increase in the defect rate after some thermal cycle. So that's all I have for the simulation. Now I will come to the conclusion part. Okay, so to summarize what we have today for the flux residue, the flux residue can lead to multiple thermal, mechanical, and electrical issues for the packaging. First, for the impact to the underfield property, it will increase the moisture absorption, lead into a decrease in the gas transition temperature and an increase in the CTE of underfield. Furthermore, for the mechanical issue, poor adhesion between underfield and the bump can come because of the flux residue, which can lead into possible bump crack and other potential reliability issues. Also, there was some paper and experiment going on that proved that the leakage current is likely to proportional to the amount of flux residue accumulated on the substrate. And nevertheless, the flux residue can impact our package process because flux residue can increase the contact angle of underfield with substrate, leading to increasing flow time, which can have a big impact under a high volume manufacturing. So that all our team have for the presentation. Our team would like to thank Dr. Tasooji and the Intel instructor for putting together this course, Fundamental of Microelectronic Packaging, and giving us the opportunity to work on this project and collaborate with an interdisciplinary team of engineers. We have here on the reference we used in the paper if any of you interested in more detail. So once again, thank you very much, Dr. Tasooji.